Beneath the soil, fungi grow through a vast network of branching threads called mycelium, and when guided in a controlled environment, this living network binds together to form a dense, rigid structure. These mycelium-based composites are emerging as highly sustainable, direct replacements for traditional plastics and legacy industrial materials. By replacing extraction-heavy supply chains with biological growth, they directly address the escalating emissions driving climate change. Instead of mining or drilling for finite resources, we can now simply grow the exact structural components we need. This transition is already moving out of the laboratory and into active production lines. This diagram illustrates the immediate sector deployment. Mycelium composites are currently taking root in two key areas: manufacturing and biomedical fields. Within these highly distinct industries, mycelium serves as the base structural material, successfully replacing conventional plastics and standard building components. This table details the first clear advantage: a steep drop in environmental footprint. Where traditional materials fail on emissions and waste, mycelium composites pass. Crucially, they match the economic viability of legacy materials. Companies can hit aggressive environmental targets without sacrificing profit margins. Adopting these composites is a viable business strategy, aligning corporate financial goals with necessary climate action. If the financial and environmental math works, we have to look at why these materials aren't ubiquitous yet. This graphic outlines 3 bottlenecks. First, intrinsic variability. Because fungi are living organisms, uniform batches are inherently difficult. This unpredictability prevents establishing standardized manufacturing guidelines. Without these standard baselines, manufacturers face the final roadblock: a lack of widespread consumer acceptance. Predictable mass market scale remains out of reach until producers reliably control the biological growth process. Overcoming these bottlenecks requires focused capital investment in research and development. That R&D must focus specifically on optimizing material properties and refining production protocols to eliminate batch-to-batch variability. The objective is a system where living organisms yield identical, standardized composite components that move seamlessly through automated, high-speed assembly lines. Once those standardized guidelines are firmly in place, these biological materials can scale globally to replace extraction-based plastics, securing a greener and more resilient industrial future.